Alright, so for our last topic for one-dimensional kinematics, we will talk about objects that are in free fall. So the first thing, though, we need to do is try and define what do we mean by something that is in free fall. So it's pretty much as simple as it sounds. I'll put some more caveats to it, make sure we all understand what I'm talking about and are all on the same page. But it's exactly what you would think it is, right? If you throw something through the air, if you drop something, for that time while it is flying through the air, that object will be considered to be in free fall, right? So now, again, we are only going to be focusing on one dimension. So at some point, we'll get to two dimensions again. Probably next week, that's what our next chapter will be. But for now, we're just going to deal with objects that are moving in one dimension. So we can throw these objects, we can drop these objects, but we're only going to throw them straight up or straight down, ensuring that they're only going to move straight up or straight down, right? And so, maybe they can move straight up and then, of course, they'll fall straight back down. But as long as they just are moving only up and down, there will be no horizontal motion to these objects for our one-dimensional kinematics free fall type of problems that we have. So as I said before, we have only gravity acting on these objects. So if I am in the middle of throwing something and it's still in my hand and I'm still pushing on it, that object would not yet be in free fall. The instant it leaves my hand, however, and then until it hits the ground or hits whatever it is I've thrown it at, during that time, then it would be in free fall. So for an object that is in free fall, we can already tell right away what the acceleration of this object is going to be. It's going to be the acceleration due to the gravity of whatever planet you happen to be on. Usually for our problems, we'll assume that we are on Earth. That's a pretty safe assumption. But occasionally, you can you can have an different force of gravity on the Moon. You can have a different force of gravity on Mars, and so on and so forth. But for now, if we're on Earth, the acceleration of our object that is in free fall, our acceleration will be written simply as 9.8 meters per second squared. So it's almost 10 meters per second squared. So again, what this means is if you drop something, right, it's what the initial velocity of that object would be zero, right? As soon as you let it go, that very instant that you have released that object, it is not in motion yet. Of course, it's going to start falling immediately, right, as soon as it can. However, after 1 second, it would be traveling at 9.8 meters per second, right, is again what we're saying. And of course, if you drop it from a standstill, it will be moving downward at 9.8 meters per second. And so another way we can write this, the shorthand that we use is we'll sometimes write this as lowercase g equals 9.8 meters per second squared. So if I ever just write lowercase g in an equation, you can rest assured that lowercase g is going to denote the acceleration due to gravity of wherever we are. In this case, when we are on Earth, it will be 9.8 meters per second squared. And again, it is important to remember the direction, right? The lowercase g is written as a positive number, but the direction of the acceleration will always be negative. So with this specified, we can then go ahead and we can rewrite all of our different equations that we have, all of our one-dimensional kinematics equations, but we can plug in something because, again, we know if something is in free fall, we already know what the acceleration has to be. So in this case, I will write delta y equals v naught times t minus 1/2 g t squared. You can use y or x for your distance. The convention, again, in this case, is just going to be to use y, right? X is denoting usually horizontal motion. It doesn't have to, but that's usually how we do it. And y is denoting vertical motion. So we're still dealing with one dimension, but instead of horizontal motion, we have only vertical motion for this case. So we'll say delta y equals v naught t minus 1/2 gt squared, right? So this is how we'll write that equation. Again, we're just saying if it's in free fall, we already know something about the acceleration of our object. Then we can also, of course, say our velocity equation as a function of time equals v naught minus gt. And then we also have, this one still works, we have delta y equals v average times t, and of course our final equation that we just derived last time, we can also say v squared equals v naught squared minus 2g delta y, right? So all these equations here will work for when our object is in free fall. So let's do some graphs again of these situations to make sure we kind of understand conceptually what this is going to look like. So let's go ahead and graph our position, our velocity, and our acceleration as functions of time assuming that we are throwing some object straight up, letting it come back down, and catching it at the same height. So let's say this. So in this case, we'll have our y-axis. We'll look at how our object moves as a function of time. We'll still have our v as a function of time. And then, of course, we'll have our a as a function of time. Let me move this up. So yeah, so if I throw something straight up in the air, as soon as I release it, it is going to start moving a little bit more slowly, right? So the slope is, in fact, going to decrease. At some point, it will get to a maximum height. And at that point, what can we say about the velocity once it's at its maximum height? When it's at the maximum height, it's going to turn around, right, and come back down. So what I'm drawing here is this nice parabola shape, but again, we have to remember this is a little bit confusing here. So we have, this is my y as a function of time. So this is not like a side view of my object. I'm not saying it's going in this nice arcing path. The actual physical path of my object is just straight up and straight back down. But the position as a function of time is it does go up and then it comes right back down to that same spot that it was. We can watch what's happening with the velocity here, right? The velocity is again, it's going to be denoted by the slope of our position graph, and the slope of this is getting smaller and smaller, right? It's kind of leveling off till it gets to here. What is the slope at the very top point? The slope at that top point is 0, so the velocity at that top point must also be 0. So for one just brief instant in time, right, when that object turns around, the velocity of that object is 0. And then, of course, it's going to accelerate back down, and it will come back down in this very symmetric manner on its way back down towards where it started. So the velocity as a function of time would look like what in this case? We'll have some positive velocity, right? And then eventually the velocity would be negative in the other direction. So we'd have our velocity as a function of time would simply look something like that, right? So we need to make sure to bring this down here. So our velocity as a function of time is going to start out positive if I throw it up, right? It'll come back down, and of course the velocity will switch over to the negative, but it'll just be this nice constantly decreasing velocity that we have. And of course the acceleration, as we know, will be, the magnitude of the acceleration will be 9.8 meters per second squared the entire time. However, it will be downward, right? It'll be down towards the Earth, which in this case we will denote as negative. Sometimes you can denote down as positive, that's okay. It's just kind of a matter of convention. Usually I'll put down as negative. That's kind of what I prefer to do, but just depending on what problems, and I'll show you some examples where you can switch it around. You can have either up or down be positive or negative, but for now we are going to use the convention where down is negative. So again, this is what the graphs look like if I throw an object up in the air, let it go to its maximum height, and then catch it at the same height that I threw it from. We have this nice symmetric case here. Sure enough, as you can imagine, right, if I throw this up at, say, 10 meters per second, this object will go up a certain height. It will eventually, it'll be decelerating the whole time. It'll be slowing down the whole time. It'll reach a point at the very top where it is no longer moving, whereas it stops and has a velocity of 0 for a very brief moment, and then of course it immediately starts to accelerate back down. When I catch it though, if I catch it at the same height, what will the velocity on the way up look like compared to the velocity on the way down? As you can imagine, the velocity on the way up will be the same speed. It'll have the same speed. Obviously, it'll have an opposite direction, though, right? Here it's going up, here it's going down, but the speed at each point will be the same. So you do have this nice symmetric case. You kind of have this symmetry of what it looks like for this object to be going up versus what it looks like when it's going down. The acceleration is the same the whole time. So if I'm slowing down from 10 meters per second to 0, then it's speeding up back to 10 meters per second, the only thing that's changing there is the direction. So we do have these nice symmetric cases that we can look at. Of course, this is if I'm throwing it and catching it on level ground. If I throw it on uneven ground, right, it would look something like this. So let's see, make sure we have this. Just to note that that is on level ground. However, let's say if I throw it up in the air and then let it fall off a cliff, right, or something like that. So I am going to let it drop to a height below where I started it from. Let's draw the graphs for those situations. So what do you think is going to happen after it leaves my hand and then comes back down and continues to fall? Well, we can tell right away. I'll tell you what the acceleration graph is going to be, right? I already know that one. Whoops, keep doing that. There it is. The acceleration, of course, is going to be the easiest one. We know our object is in free fall, so it is going to be constantly accelerating downward at negative 9.8 meters per second squared. The position graph will look very similar, right? At least at first. So we'll start out like this. We'll go in our, we'll go straight up. We'll come straight back down, and then we will pass beneath where we started before. So of course, then the velocity graph will look very similar, but basically we'll just we'll end up going even faster on the way down compared to what we were doing before that, right? So if I were to throw it on uneven ground, again, you can imagine this as we're standing at the top of a cliff. We throw something straight up right at the edge of the cliff. It passes, it goes up to its highest point. It passes back to where we are standing at the edge of the cliff, and then continues to fall down the side of the cliff. It'll just move like this, right? So we still have this symmetric case for this situation here as it goes up and comes back to where it was, but then of course it will continue to speed up and go back down towards the ground that way. Again, the velocity will just continue to increase faster and faster as it gets to the bottom. But for this first part, you do have this still symmetric case, right? Another interesting thing that we can point out about this is, let's say I throw it up at, again, 10 meters per second. When it comes back down and when it comes past me, it will again be going 10 meters per second, right? So the speed that it will have when it gets to the bottom will actually be the same as if I'd thrown this just straight down at 10 meters per second, right? Of course, the time will be different, right? We'll have some extra time that it spends going through this arc, but if I throw something up at 10 meters per second versus if I throw it down at 10 meters per second, the speed at the bottom will be the same no matter what, again, because of this kind of symmetric case that we have here, where this first part, again, this will add more time, but we have the symmetric case up, it'll come up at the same speed that it comes back down at for the same corresponding height. So yeah, so that's just kind of a conceptual overview of some of these problems. Hopefully by the time you see this video, I will have a video of several examples worked with some of these free fall problems. We'll have some more kinematics problems as well. If not, make sure to harass me about that and I will put that up for you guys.